So after all this work that we've gone through, we've seen how to design control systems, we've seen how to take different controllers and put them together in a hybrid navigation architecture. We've seen how to deal with practical issues like the fact that obstacles are indeed not points, and that we're never going to be able to measure exactly where we are, so we need to fatify the guards. We have tweaked our parameters. We're actually ready to do it for real. So the presentation or slide part of this lecture is very short. It's this. Enough talk. Let's do it. So now we are indeed ready to see all our hard work pay off by deploying these rather elegant algorithms that we developed on the actual robots. And as always, I'm here with JP Delacroix, and we are going to take our old friend, the Kepira differential drive mobile robot, through a series of obstacle courses where the obstacles become more and more complicated. And as you can see, the first setup is a convex obstacle. We saw in the lecture that in theory, the robot can actually get stuck in one of these local minima where the go-to-goal and obstacle avoidance behaviors will cancel each other out. In practice, for an obstacle of this size, that ain't going to happen because the world is indeed a noisy place, and the noise will always kick the robot out of these particular local minima. So what we're going to see first is go-to-goal and avoid obstacles, and together that should be enough to have the robot navigate this single convex obstacle. So as we can see, the robot starts in a go-to-goal behavior. It approaches the obstacle, and there the infrared sensors picks up the obstacle, and the robot successfully navigates around it. Now it's safe to go back to go-to-goal, and as we can see, the robot successfully managed to navigate this particularly simple environment with only 2 behaviors. So now let's take our 2 favorite behaviors, go-to-goal and avoid obstacle, and set them up to fail. As we saw in the lectures, there's really no way for these 2 behaviors to successfully negotiate a non-convex obstacle. In this case, we have a cul-de-sac that we will try to get around using only these 2 behaviors, but we are not, to be completely honest, expecting this to go all that well. So the robot starts out in a go-to-goal mode, and it is entering the cul-de-sac, and it's going to start avoiding the obstacles here, but it doesn't quite know where to go because it's pulled away, but the goal-to-goal is pulling it forward, and the poor robot is completely confused and really has no way of punching its way out of this cul-de-sac with only 2 behaviors. And as we can see, the end result is somewhat disastrous. So that was rather depressing. The poor robot was stuck in the cul-de-sac without really anywhere to go, and obstacle avoidance and go-to-goal kept pulling it in different directions, and it ended with a mild disaster. We have now seen in the lectures that the way around this problem is really to introduce a 3rd behavior, the induced mode, follow wall, which will allow the robot to purposefully make its way out of the cul-de-sac, and once it has a clear shot to the goal and sufficient forward progress has been made, follow wall will be released and go-to-goal will again take over. So JP, let's see the grand finale here with a full-blown hybrid navigation architecture in action. The robot starts out again in a go-to-goal mode and enters the cul-de-sac. And what's going to be different now is the obstacle avoidance is going to be replaced by a follow wall, and the robot purposefully makes its way out of the cul-de-sac along one of the obstacle arms. And as you can see, the problems we had before with confusion and being pulled back and forth between the 2 different behaviors is no longer there. Now the robot has successfully navigated around the obstruction and is back into the go-to-goal behavior.